Hi everyone, today we're going to be looking at the material for assignment 45. I noticed the homework, like it was for assignment 44, is a worksheet, but I kind of want to start with actually some bell work questions for you. So here's the first question. 1. What happens on the graph of a polynomial when a factor has an even multiplicity? Okay, what happens on the graph of a polynomial when a factor has an even multiplicity? Think about that, come up with an answer. If you watched the video for assignment 44, you should be very comfortable with this. Okay, so what happens when a factor has an even multiplicity? There is a bounce, and I don't know if it's a bounce up or a bounce down. There's a bounce up or down off the x-axis at the x-intercept created by that factor. Okay, so if I see y equals x minus 3 with an even multiplicity, I know that at x equals 3, there's going to be a bounce. Okay, there's the first question. What happens on the graph of a polynomial when a factor has an even multiplicity? 2. How would the graph be different if the factor had an odd multiplicity of 1 versus an odd multiplicity of 3? What's the difference on the graph between whether we have a 3 here or a 1 here? Okay, so take a minute to think about that and come back, because I can't wait to go more with you. All right, so what do we know? Multiplicity of 1 means the graph passes through just passes straight through, but a multiplicity means we wiggle through, like y equals x to the third or y equals negative x to the third. Okay, so even multiplicity is a bounce, and odd multiplicity is a wiggle. Good. Graph with x and y intercepts an appropriate end behavior. This polynomial, x minus 1 squared, x plus 3 to the third, and x minus 4. Please don't forget x and y intercepts an appropriate end behavior, and I need to see the appropriate behavior based on the multiplicity of the factors at each of the zeros for this polynomial. Okay, pause the video, give this one a try. I can't wait to see what happens next. Hey, welcome back. This is x squared times x to the third times x to the sixth, so I know both ends go up. I see x-intercepts at -3, at +1, and at +4. Now, what happens at -3? A wiggle. Is it going to be this wiggle? No, because this can't connect to that. I have to wiggle like a -x to the third. Now, what's happening at x equals 1? A bounce. And at x equals 4, I'm just going to pass through. Okay. Don't forget the y-intercept needs to be labeled here. And I find a y-intercept by setting all these x's equal to 0. And so what am I going to get? I'm going to get 1, I'm going to get 27, and I'm going to get -4. So 27 times -4 is -108. And there's my graph. Now, I thought it might be good for us to practice this a little more, okay? And I think if we're okay with that, then maybe we can step it up a bit. So, let's see what we've got. How about y equals x minus 1, x plus 3 squared, and x minus 4 to the third. Please graph this one now. Pause the video, give it a try. Hey there. Did you find the x-intercepts at -3, +1, and +4? Good. Did you notice that this was a 6th degree polynomial with a positive leading coefficient? So it goes up on the ends. Did you notice that at -3 we're supposed to bounce? And that at +1 we're going to pass through? And what are we going to do at 4? We're going to wiggle. Can it be this wiggle? No, because that won't connect with that. It has to be this wiggle. And don't forget to label the y-intercept. We find the y-intercept by setting x is equal to 0. So I'm going to have -1 times 9, which is -9, times -64. 4 to the third is 64. So 9 times 64. 6, is it 576? Yes, it is 576. And this is a negative, this is a negative, so this is going to be a positive 576. All right, well, that's great. How about this one? Y equals 1 minus x squared, x plus 3 squared, and x minus 4. Okay, think about this one, and come back in a few minutes when you have it graphed. Okay, welcome back. 2, 4, 5th degree polynomial. But wait a minute. Is it a negative or positive leading coefficient? Well, this is going to be negative times negative, which is positive. So this is still going to be a positive 5th degree polynomial. So I'll start with the appropriate end behavior. -3, 1, and 4. What am I doing at -3? I'm bouncing. Bounce. At 1, I'm also bouncing. Bounce. And at 4, I'm passing through. What if instead we had this? So now I have -x times -x, which is positive x squared times positive x squared times positive x, and got positive x to the 5th times a negative. How does that change things, having that negative out in front there? Well, no problem. Now I've got a negative x to the 5th, so this ends up going high, and this goes low. At 3, I'm still supposed to bounce. At 1, I'm still supposed to bounce. And at 4, I'm supposed to pass through. Don't forget to label the y-intercept. So if I plug a 0 in there, and a 0 in there, and a 0 in there, and a negative here, I get 9 times 4 is 36 times 1 is 36. And before we had that minus there, just when we have this one, now I've got -4 times 9 is -36 times 1, and that's going to be 0, -36. Okay? So pay attention to whether you have an even or odd degree. but also pay attention to whether or not you have a positive or negative multiplicity. I'm sorry, positive or negative leading coefficient. Now, I'd like to make these a little less algebra 2 and a little more pre-cali. Okay? So what if I told you that a is a number between 4 and 1? Now, you don't decide what number it is. It's just some number in between 1 and 4. Not equal to 1, not equal to 4, but between them. Okay? I'm giving you that piece of information because I'm showing you that our next polynomial is going to be x minus 1, x minus a squared, x minus 4. Okay? See, a. Now, when I look at this problem, I see x times x squared times x, that's x to the 4th. I have a positive times a positive times a positive, so I have a positive leading coefficient. I know the ends both go up. Where are my x-intercepts? At 2, at a, and at 4. Well, I'm okay with, I'm sorry, not 2, but 1, a, and 4. I'm okay with those, but what about a? Where does it go? Well, a is a number between 1 and 4. So I could put it here, I could put it here, I could put it here. Just somewhere between 1 and 4, I'm going to put an a. It doesn't really matter where. You could make it halfway, but it doesn't have to be halfway. Okay? So what do we know? This end is up. This end is up. I see a multiplicity of 1, so I pass through. I see a multiplicity of 2, which means when I get to a, I have to bounce, and a multiplicity of 1, which means I pass through. And there's my graph. Now, because I know that a is between 1 and 4, I know that this goes further and gives me a place to draw my y-intercept. Now that's interesting. What happens when I plug a 0 in? Well, negative times negative is positive 4, and negative a squared is positive a squared, so my y-intercept here is 0, 4a squared. Yes, you need to label the y-intercept. Yes, I got this by plugging a 0 in for all the x's. Negative 1 times positive a squared is negative a squared times negative 4 is positive 4a squared. Okay, and there's my graph. So, now that we know that a is a number between 1 and 4, will you please graph y equals x minus 1 squared x minus a and x minus 4 to the 3rd. In fact, I think I want an odd, so I'm going to go with a 2-bit. All right, give it a try. All right, welcome back. 7th degree polynomial with a positive leading coefficient. There's the end behavior. I have zeros at 1, at a, and at 4. What am I doing at 1? I'm bouncing because of the even multiplicity. What am I doing at a? I'm bouncing because of the even multiplicity. And then what am I doing at 4? Because of this, I'm wiggling. Am I going to wiggle like this? Well, how could I connect that with that? No, it can't be that wiggle. It has to be this wiggle. Here we go. And don't forget to draw, to label the y-intercept again. 0, 1 times negative a is positive a squared times negative 4 to the 3rd is negative 64. So I end up here with 0, negative 64a squared, right? A got squared. Doink. And there we are. There's our graph. Okay? I would expect something like that, certainly on a pre-calc quiz or test. All right, so the textbook at this point would ask this question. It's kind of a free and open-ended thing. They say, write a polynomial equation where n equals 3, and remember n is the degree, with zeros at x equals 3 and x equals 5. Okay, so they're not saying graph, they're just saying polynomial equation. So I'm going to turn these x-intercepts into factors. And so I get this. But wait a moment. If I FOIL this out, I get x squared, and I'm told here it has to be x to the third. So now it's x to the third. Or now it's x to the third. Okay? I can't add more factors because it told me where all the x-intercepts are. But I can apply multiplicity to my factors in order to meet these preconditions. So what if I have, instead of 3 here, I have a 4? Well, I could have 2 and 2. I could have 3 and 1. Or I can have 1 and 3. Okay, I just need the degree to be 4. And I need these to be the only x-intercepts. All right, will you try this one? Write the equation of the polynomial where degree is 4 and has zeros at 2, 0, and negative 1. Okay, so give it a try. Shouldn't take you very long. Okay, so fourth degree polynomial. Y equals x minus 2, x minus 0, x minus minus 1. So when I tidy that up, I see x minus 2 times x plus 1. You could leave this over here, that would be fine. I just usually bring it out from. But wait, x times x times x is x to the third, and we're told we need a degree of 4. So what are you going to do about that? That's right. Maybe this one gets squared, and now I have a fourth degree polynomial. Or maybe this one gets squared, and now I have a fourth degree polynomial. Or maybe this one gets squared, and then I have a fourth degree polynomial. So I've got 3 different choices for that one. All right. What happens if I change my zeros and degree? So degree of 2 with zeros at x equals 1 plus root 3 and x equals 1 minus root 3. Now, don't tell me you don't know what to do here, because when we had x-intercepts at 2 and x-intercepts at 4, you said x minus 2 and x minus 4. This is not going to be any different with these x-intercepts. It's going to be x minus 1 plus root 3 and x minus 1 minus root 3. Right? I just shove those zeros into these binomial parentheses, binomial terms, just like I had when I had x equals 2 and x equals 4. I did x minus 2 and I did x minus 4. All I'm doing is plugging the zeros into this format. So all I'm going to do is take these zeros and plug them into that format. Now you may want to tidy this up where you distribute that negative and distribute that negative, and you'll end up with x minus 1 minus root 3 times x minus 1, negative times negative is positive root 3. And look, this is why we practiced foiling trinomial with trinomial, because we see it here. All right? Graphing this, you know, that's an x-intercept, that's an x-intercept. Mr. Goop, I don't know what root 3 is. Well, I hear you, but I know that root 3 is between root 4 and root 1. And this is 1, and this is 2. So this is a number between 1 and 2, and it's closer to 2. Okay? So 1 plus almost 2. So 1 plus root 3. And then this one, 1 minus root 3, well, that's almost 2. 1 minus almost 2 is going to be over here in negative land, 1 minus root 3. And degree 2 with these x-intercepts, it could be this polynomial, but they don't tell me anything about positive or negative leading coefficient. So we could also have this polynomial. Degree 2, 2 x-intercepts. They're not asking me to graph it. They just want me to say y equals x minus the first x-intercept times x minus the second x-intercept. That's it. So I get y equals x minus 1 minus root 3, x minus 1 plus root 3. Please don't waste your time foiling this in these problems, please. All right, now notice these irrational ones, because they had square roots, they came in conjugate pairs. Irrational roots always travel in conjugate pairs. So if I have something like y equals x squared minus 3, and I asked you to find the x-intercepts of this, you would set y equal to 0, and then you would add 3 to both sides, and then what? And then, to get rid of the x, the squaring on the x, you would take the square root, and what do you need to remember? Plus or minus. Look, we have an irrational, a radical number, an irrational root, and it came in plus and minus pairs. So whenever we have radicals in our answer, we're going to get plus and minus pairs in our class. So, will you write the 4th degree polynomial with zeros at x equals root 2, x equals negative root 2, and x equals 1. Give that a try and come back when you're done. All right, so my only concern is that you think about x minus root 2, x plus root 2, and x minus 1. I think that's a great start. Okay? That's a great start. It works all these x-intercepts into factored form. But we want a 4th degree polynomial. If I put my 2 here, I have x squared times x, no problem, I get x to the 4th. But what if I put my 2 here? Does that still work? Well, that's still going to be x squared times x, it's still going to be x to the 4th. And from a graphing perspective, negative root 2, 1, and root 2. This is a number between 1 and 2, bigger than 1. So this is bigger than 1. And in this situation, I'm bouncing at negative root 2, passing through at 1, and passing through at positive root 2. So, oh, and don't forget, 0 is going to be 2 times negative 1 is negative 2 times negative root 2 is positive 2 root 2. What an interesting y-intercept. So yeah, that's all I need to do when I go backwards like that. When I try and write the equation like that. Speaking of writing the equation, what if I give you a graph? Can you write the equation of the polynomial? So, let's see. Here's my graph. This is 1, this is 5, this is negative 2, and I have a y-intercept located at 10. Okay. So how do we go about writing the equation of this? Well, the first thing I know is that I can make that into a factor, I can make that into a factor, I can make that into a factor. X minus and minus 2, x minus 1, x minus 5. Good. But I need an a value. There could be stretching, there could be compressing. I don't know until I check. And that's what this point is for. If I plug in the ordered pair 0, 10, what happens? Well, I get 10a equals 10. So I know a equals 1. So there's my polynomial. But if I had here 40, then I would say 40 equals 0 plus 2. Oop, I lost my a. 0 plus 2, 0 minus 1, 0 minus 5. And so look what happens. Negative times negative is positive 5, times positive 2 is positive 10. I get 10a equals 40. And then when I divide both sides by 10, I get that a equals 4. And so in this situation, I have to have 4. And oops, not that one, this one. And so there we go. 4, x plus 2, x minus 1, x minus 5. There's my polynomial. Now, we also need to be able to take into consideration bounces and wiggles here. So if I have this graph, 1, 5, negative 2, and 0, negative 20. Okay, so can we write the polynomial here? Well, y equals a, x minus and minus 2, x minus 1, x minus 5, and if I tidy that up, that's a plus 2. Now I notice I have a 4th degree polynomial, but if I FOIL this out, I only get x to the 3rd, and I see a bounce. So how does that bounce at 1 change this? That's right, an even multiplicity on the x minus 1 factor. Are we done? No, there's still that a value. Luckily I have this y-intercept to plug in to help me solve for a. So what are we going to get here? 1 times 2 is 2, times negative 5, negative 10a equals negative 20. So a equals 2. 2. And there's my polynomial. Feel like you can do it? Well, let's practice and see. Oops, it's supposed to come back up again. There we go. Okay, that's negative 2, that's positive 1, positive 5, and here we have a y-intercept of 0, 80. All right. I know because both ends go up, this is an even degree polynomial with a positive leading coefficient. But I don't know what that a value is yet, and I have to think about writing the equation for this. So pause the video, write the equation for this, come back, and we'll take a look together. All right, did you start by saying y equals a, x minus and minus 2, x minus 1, and x minus 5? Because that's how I started. But then I looked over here, and what do I see at x equals negative 2? It's not a wiggle, it's a bounce. And that means I need a multiplicity of 2 here. So now I have x squared times x, that's x to the 4th. Good, both ends go up. Now let's find our a value by plugging in this extra point. a equals a, 0 plus 2 squared, 0 minus 1, 0 minus 5. So negative times negative for positive 5 times 2 squared is 4. 5 times 4 is 20. A equals 80. Oh, so a equals 4. So I'm just going to plonk a 4 in there, and I'm all set. All right? How about this one? How about here's 1, here's 5. Oh, I guess I want to change these. How about this is 2 and 4, and over here we have negative 3. And this point, sorry, I'm going to negative, or else I won't know what the y-intercept is supposed to be without a whole lot of thinking. So this is 0, negative 16. Okay, please write the equation for this polynomial. Is it even or odd degree? What do you think? I think even as well. Come back after you've given it a try, and we'll compare answers. Did you start off with y equals a, x plus 2, x minus 1, x minus 4? That's great, but that's only a third degree polynomial. We need a fourth degree polynomial. Do I make this one squared? No, there's no bounds at 1. Do I make this one squared? No, there's no bounds at 4. There is a bounce at negative 2, and so I have to put a 2 there. I need a bounce at negative 2. Am I done? Not done yet. I still need to plug in these points. So negative 16 equals a, 0 plus 2 squared, 0 minus 1, 0 minus 4. 2 squared is 4. Negative 4 times negative 4 is positive 16. So I have 16a equals negative 16, which means a equals negative 1. There's my polynomial. Please don't even think about foiling these out. That's so algebra 2. All right, so what about this one? What if I, and then I, and then I, and this is 2, and this is 1, and this is negative 1, and down here I've got negative 12, 0, negative 12. Please write the equation for this polynomial. Welcome back. So I started with y equals a, x minus a minus 1, x minus 1, x plus 2. Actually, I know minus a minus is going to be a plus, so I started that way. Now, this is a third degree polynomial. Is this the end behavior for a third degree polynomial? No, it isn't. So, what do we have? We have an even degree polynomial, because both go up. I guess the smallest degree I could have is 4, except what's happening at 2? There's a bounce. And what's happening at negative 1? There's a wiggle. I have to pay attention to what's happening at each 0 so I can make the multiplicity be what it should be to create those events. Now, I still need to plug this in. So, negative 12 equals a, 0 plus 1 to the third, 0 minus 1, and 0 plus 2 squared. So what are we going to get? 1 to the third is 1, times negative 1 is negative 1, times positive 4 is negative 4. Negative 12 equals negative 4a. If I divide both sides by negative 4, I get a equals 3. So I plug my 3 in there, and that's my equation. Okay? Gotta have those multiplicities, and you gotta be thinking about even or odd. Both ends go up, even. One goes up, one goes down, odd. Okay? Excellent. All right, one last one of these going backwards problems. So what's going to happen here? Okay, I've got this, and this, and that. This is 3, this is 1, this is negative 2, and this is 0, negative 24. Okay, please write the equation for this polynomial. And it is the equation. It's not just a equation, it's the equation. Okay, welcome back. So, y equals a, x plus 2, x minus 1, x minus 3. Right now we have a third degree polynomial, but we've got the end behavior of an even degree polynomial. So what do you notice? Well, I notice here a wiggle, so this is a 3. And I notice here a bounce, so this is a 2. 3 plus 2 plus 1 is 6. I have my even degree polynomial. But wait a minute, is this it? What about my a value? Let's plug in our negative 24. A, 0 plus 2 to the third, 0 minus 1 squared, 0 minus 3. And let's see what we get. Negative 3 times 1 is negative 3. 2 to the third is 8. Negative 3 times 8 is negative 24. Oh, look at that. A equals 1. I won't know that unless I plug in that y-intercept or some other point to help me find my a value. I should always assume there's an a value, because if I don't, well, I'm not going to look for it. All right, so what's next? Well, next is, how are you going to graph this? Graph. Y equals 3x to the third minus 15x squared plus 18x. I did it for you in the last video. You do it for me now in this video. Come back when you're ready to talk about it. So what I said in the last video was I was going to factor out a GCF from each of these terms. And so I'm left with x squared minus 5x plus 6. This is factorable as x minus 2, x minus 3, and here's a 3x in front. Each of these factors has a multiplicity of 1, so I know I'm passing through at 0, because remember that's x minus 0 to the first. I'm passing through at 2, and I'm passing through at 3. And this is a positive x to the third, so this end is down, and this end is up. Woo! There's my graph. Now, what about this one? Y equals x to the third minus 8x squared plus 16x. Can you graph that one for me? Give it a try. Come back when you're done. Okay, so did you factor out an x? I did. I find these problems are much easier if I always remember to do GCF factoring first. Ooh, look, a trinomial. Does it factor? Sure does. X minus 4 times x minus 4 times x. And you might find it easier to write this like that, because this doesn't necessarily scream bounce the way this does. And I put this like this to remind you that there's an x-intercept at 0. So we have an x-intercept at 0, another one at 4. This is a positive third degree polynomial, so this end is down and this end is up. At 0, I have a multiplicity of 1, so I'm just going to pass through. But when I get to 4, I have that squared, which means I'm bouncing there. Okay, there's my graph. Look, my x and y intercept is at 0. Okay, so the very last thing I want to do with you is take a look at a word problem. And this is actually a word problem that we first saw in the last, we first saw in our functions unit, in the function applications assignment. So here I have a square sheet of tin with 36 inches on a side, and I clip out little squares from each corner, and they're squares, and they're all the same square, x by x, x by x, x by x, x by x. Okay, so I'm going to take out these squares, cut them out, off you go, by squares. And then I'm going to fold along the dotted lines, and that's going to turn into an open-topped box. Okay? So, 1. Write the equation for the volume of the box as a function of x. Now I know that volume is length times width times height. But what are those? Well, think about this over here if you've forgotten the example that we did in the last unit. This distance is here. Now I know this whole distance is 36, but I took away x and I took away x, so how much is left here? That's going to be 36 minus 2x. Cool. What about this? Well, that's here. I know that this distance is 36. I know this is x, and this is x, and I'm taking those away from the 36. So what's left over here? What would this length be? Well, the whole side 36 minus 2x again. Great. Now what about the height? This height is here. When this folds up, it matches this as it folds up, and so we know that's x. So I can write volume as a function of x by doing length 36 minus 2x times width 36 minus 2x times height x. Now I like looking at this as v of x equals x times 36 minus 2x squared. Because the second thing they ask me to do is to graph v of x and graph v of x. Yeah, that's all I'm going to do right now. Graph v of x. So here's my v of x. Where are my x-intercepts? What's the degree of this polynomial? Is it positive? Is it negative? Well, this is going to be negative 2x times negative 2x, positive 4x times x, positive 4x to the third. So I know that this end goes down and this end goes up. Excellent. With zeros where? Well, I know there's a 0 with 0. What about here? 36 minus 2x equals 0. 36 equals 2x. So x equals 18. And what's happening at x equals 18 according to this multiplicity? That's right, I'm bouncing. So I'm going to come up here and pass through 0 and bounce off at 18. Alright, so there's the graph of volume. Now, let's continue this conversation. Graph of volume. For step 3, what's the domain of v of x? Now, often when we see a third-degree polynomial like this, and remember our v of x was x times 36 minus 2x squared, often when we say, oh, I've got a polynomial, I know the domain of a polynomial is all real numbers. But is that true in this case? Passing through and bouncing. 0, that's 18. Well, I would argue no, because this is a real-world thing. This equation represents the volume of this box. Can I have a box with a volume of 0? No, that has to go away. And can I have a negative volume? No, so no negative volumes. Now, these are all positive volumes here, well, except at 18 where I have that 0 volume again, so that's not going to be any good. I want to include that point. But what about points after 18? The volumes are all positive numbers. What if I plug in a 20 here? Okay, 20 times 36 minus 2 times 20. 2 times 20 is 40. 36 minus 40 is negative 4. Can this side and this side be negative 4? No, they can. And so anything past 18 is going to create negative side lengths. And that's not going to be okay. So I have to throw that away as well. So it looks like my domain goes from 0 to 18. And I had to think about the real-world implications of that to this problem. Okay? Now, the last thing I want to ask is, what value of x makes the maximum volume? Remember, we started by talking about cutting out little x by x squares from each corner. And I wasn't sure how big those squares should be. Well, now, if I find the maximum here, that's the x value that produces the maximum volume. That will tell me how large to cut these out. We know x has to be a number between 0 and 18. But what number? Well, I want to say something about this, because when we had problems like this, when we were dealing with quadratics, the vertex was always halfway between the x-intercepts, which would mean when x equals 9, I would have a maximum. Well, let's take out our calculator, and let's see what the graph tells us. So, y equals, and our equation is x times 36 minus 2x, and 2x, and don't forget the squaring in that factor. Okay, so I've got x times 36 minus 2x quantity squared. Alright, now I know my viewing window should go from 0 to 18 with the x's, so I'm going to set my viewing window to go from 0 to 20. Steps of 2. What about the y values? Well, this is a cubing function. Y equals x to the third. And if I take something like 20 and cube it, it's 20 times 20 times 20. That's 8,000. So I'm going to go from negative, well, it's volume of the box, and I don't have any negative volume. So I'm going to go 0 to 8,000 in steps of 8,000. Graph. Okay, it looks just like our graph. And I'm looking for this maximum. Does it look like that maximum happens halfway between 0 and 18? No, it doesn't. If I do second calculate maximum and move that cursor to the left of the maximum and hit enter, and then move the cursor to the right of that maximum and hit enter, and no, I don't want to guess, I see that my maximum occurs. Where is that? That's located at 5.99999. Hey, guess what? That's 6. And the maximum volume I'm given is 3, 4, 5, 6. That's kind of a freaky volume. It really is that. That's cool. Alright, so my maximum volume occurred when I cut 6 inches out of each corner. Not halfway between 0 and 18. It's almost never halfway. So how am I supposed to find that point? Right there, I had to use my calculator. Well, it turns out that there is a way to find that maximum occurring at x equals 6, but it requires us to use calculus. So, if you're ever asked to find a maximum or a minimum on a polynomial, you graph it on the calculator and you second calculate max or second calculate min. That's how you're supposed to find maxes and mins. Please don't guess that it's halfway between, because it probably won't be halfway in between. Alright, that's lots of stuff that we covered. We reviewed graphing with multiplicity. We learned if a was a number between 4 and 1, that we could graph something like x minus 1 squared, x minus a to the third, x minus 4. And so we would say, okay, 1, a, 4, bounce, wiggle, pass through. Smooth curve. Okay, and a y-intercept over here at 0, what? Well, this is negative a to the third times negative 4, so it's positive 4a to the third times positive 1, so I have 4a to the third there. What I've noticed is on quizzes and tests, when people are asked to graph these things, they graph this fine, and even this fine, and this fine, and they leave that out. Please don't leave out the the y-intercept on these graphs. We wrote the equations given degree and zeros, and then given an equation, given a graph, you went backwards and were able to tell me what equation would make that graph. I thought that was really cool that you could do that. And then finally, we had some unfactored polynomials, and we learned that we really needed to factor those polynomials first before trying to graph. All right, well, tonight's homework is another worksheet for assignment 45, writing equations of polynomials. And so you'll find that in our Office 365 team. All right, take care, everybody. Hey, don't forget to ask questions.